good Datta education. In this video, we are going to learn about modern physics, atomic spectra, and models inadequacy of classical physics, chapter 1, 1.1.2, photoelectric effect. Photoelectric effect. In your exam, a long answer type question discuss in detail on photoelectric effect is given. Then you need to write a following answer so that you will be getting your full score. Answer: the emission of electrons from a metal plate when illuminated by light or any other radiation of suitable wavelength is called photoelectric effect. The emission of electrons. That means electrons are emitted onto a metal plate so that when illuminated by light or any other radiation of suitable wavelength to the emission of electrons, then the total phenomenon is known as photoelectric effect. The emitted electrons are called as photoelectrons and the phenomenon is called as photoelectric effect. The circuit representation to observe the photoelectric effect is shown in figure 1. Here we can see the circuit diagram in order to detect or see the photoelectric effect. The circuit consists of a discharge tube with two electrodes connected to variable voltage V with two electrodes. The time interval between arrival of light and emission of photoelectrons at a metal surface is 0. Here the time interval between arrival of light and emission of photoelectrons at a metal surface. Both we are making to fall on the metal surface. So it is 0. That means at the correct time the light and emission of photoelectrons is upon the metal surface at the same time on the metal surface. But the photoelectron requires a period of time to accumulate the energy before leaving the metal. The photoelectron requires a period of time. That means when we are emitting a photoelectron, it takes some time to travel into the metal so that accumulate the energy before leaving the metal. So it need to accumulate energy before leaving the metal. So it gets some time, period of time is required for a photoelectron. After accumulation of enough energy, the photoelectrons get illuminated from the surface of a metal plate. After accumulation, the photoelectrons get illuminated from the surface of metal plate. Anode to reach the cathode and produce the necessary amount of current so that these photoelectrons after accumulation gets illuminated to the surface of metal plate and travels from anode to cathode by producing necessary amount of current. When V is increased to V0. When V is increased to V0, we can see this flow of electrons, or else the produce the necessary amount of current. The production of current is shown between when V is increased to V0. Photoelectrons get repelled due to their low energy before reaching the cathode. Photoelectrons get repelled, that means gets back due to their low energy before reaching the cathode, he is telling. This results in the decrease of current gradually to 0. Because of this repulsion of photoelectrons, this results in decrease of current gradually to 0. When V equal to 0, photoelectrons possess maximum kinetic energy. When V equal to 0, the photoelectrons will give maximum kinetic energy. At constant frequency, the photoelectrons are more for bright light than dark light but possess same electron energies as shown in figure 2. That means at constant frequency the photoelectrons are more for bright light than dark light but possess same electron energies, whether it is a bright light or dark light, but possess the same electron energies at constant frequencies. Here is the graphical representation. Hence, the stopping potential is independent of the intensity of radiation and the saturation current is proportional to the intensity of incident radiation. Higher is the intensity of incident radiation, higher is the saturation current. Hence, the stopping potential. The potential which is stopping is independent of intensity of radiation. How much the intensity of radiation is not calculated for the stopping potential, and the saturation current is proportional to, here saturation current is proportional to the intensity of incident radiation. Higher is the intensity of incident radiation, higher is the saturation. That means if intensity of incident radiation is increasing, the high saturation current is also increasing. That means they are equal. Intensity of incident radiation is equal to saturation current. At constant intensity of light, the photoelectrons above critical frequency V0 possess maximum energy, while below V0 photoelectrons above critical frequency is V0 again possess maximum energy, while below V0 possess low energy, no emission of electrons. In figure 3 we can see there is no emission of electrons at constant intensity of light. When intensity of light is constant, everything remains V0. Here we have a subheading for this long answer type question, that is quantum theory of light. Einstein proposed quantum theory of light, which assumes that light is absorbed and carried by the waves in discrete packets of energy called photons. Here we can see what are photons. The image of photons here. Einstein gave an assumption that the light is absorbed and carried by wave packets or waves in discrete packets. The waves are which assumes that light is absorbed and carried by waves in discrete packets of energy called photons. That means the wave is travelled or carried by discrete packets, and these discrete packets are named as photons because light is emerged into this discrete packet, so that this will be carried, so that these discrete packets are called these discrete packets of energy called photons. According to Einstein's hypothesis, as the electromagnetic wave EM wave energy is due to photons only, the photoelectrons are emitted without any delay. What Einstein is telling is electromagnetic wave energy is due to only photons. That means because of photons only, the photoelectrons are emitted without any delay. When photons are moving, then photoelectrons are easily emitted without no delay. The change in the intensity of photoelectron does not affect their energies. The change in the intensity of photoelectron does not affect their energies, he is telling. As the frequency increases, the photon energy h nu increases, thus resulting in higher energy photoelectrons. As the frequency increases, the photon energy h nu is increasing, then which results in higher energy photoelectrons. Frequency increases, photon energy h nu increases, then at last we get the output higher energy photoelectrons is our output. The photon's energy is used in two parts. Part 1. A part of its energy is used to free the electron from the atom and away from the metal surface. This energy is known as photoelectric function, photoelectric work function of the metal, and is denoted by W0. The other part is used in giving kinetic energy half mv square to the electron, so that by adding these two we get h nu, the photon energy. W0 h nu equal to W0 plus half mv square. H nu equal to W0 plus half mv square, where v is the velocity if emitted electron, and the equation is known as Einstein photoelectric equation. This equation is given by Einstein, so that this is said to be Einstein photoelectric equation. H nu equal to W0 plus half mv square. Here we can see the graphical representation upon frequency versus maximum photoelectric energy. For calcium it is at 1 point, for sodium it is varying, and for the cesium it is varying. From the as the frequency changes, their maximum photoelectron energy changes. This is our end. With this we end our question, long answer type, followed by we are giving an example question for photoelectric effect. For example, in your exam, he is asking a following to solve the question in this way. The threshold wavelength for photoelectric emission in tungsten is 230 nanometer. What wavelength of incident light must be used in order to eject electrons with a maximum velocity of 5 into 10 to the power of 5 meter per second? Given for a photoelectric emission in tungsten, threshold wavelength lambda naught equal to 230 nanometer. We are writing what is given in the question. Here it is given that photoelectric emission in tungsten, threshold wavelength lambda naught equal to 230 nanometer, maximum velocity of ejected electron Vmax equal to 5 into 10 to the power of 5 meter per second. According to Einstein's photoelectric equation, what is our equation? H nu equal to W0 plus half mv square. Here v square is written as Vmax half mv square max equal to h. Here nu is further written as nu minus nu naught. Then half mv square max, half mv max square equal to h into c into 1 by lambda minus 1 by lambda naught. Why? Nu is equal to c by lambda. C is light, lambda is wavelength. So we are converting nu into c by lambda in the second step. Hc into 1 by lambda minus 1 by lambda naught. We are substituting our values. Half into 9.1 into 10 to the power of minus 31 into 5 into 10 to the power of 5 whole square. Here m value, the mass value is 9.1 into 10 to the power of minus 31 for which mass? Tungsten mass. Then Vmax value is already given in the question. Velocity of ejected electron Vmax equal to 5 into 10 to the power of 5 meter per second. Equal to 6.626 into 10 to the power of minus 34 into 3 into 10 to the power of 8. As we all know, H Planck's constant is 6.626 into 10 to the power of minus 34. Then C, velocity of light value is 3 into 10 to the power of 8 into 1 by lambda minus 1 by 230 into 10 to the power of minus 9. That means 1 lambda naught is considered as 230 into 10 to the power of minus 9. After substituting it by calculating, we got our LHS as 113.75 into 10 to the power of minus 21 equal to 6.626 into 10 to the power of minus 34 into 3 into 10 to the power of 8 into 1 by lambda minus 1 by 230 into 10 to the power of minus 9. That means LHS is calculated, RHS remains the same. Then here we are changing our 1 by lambda onto LHS side. Then we are taking the whole bracket 1 by lambda minus 1 by 230 into 10 to the power of minus 9 onto the LHS side. This before LHS is taken upon the numerator on the RHS side, and this RHS side is taken as the denominator. One by lambda minus 1 by 230 into 10 to the power of minus 9 is equal to 113.75 into 10 to the power of minus 21 by 6.626 into 10 to the power of minus 34, 3 into 10 to the power of 8. Then in the next step we can see 1 by lambda minus 4.348 into 10 to the power of 6 is equal to 5.72 into 10 to the power of 5. Then again we are sending our minus negative value in the LHS to onto the right hand side, which became a positive. 1 by lambda equal to 5.72 into 10 to the power of 5 plus 4.348 into 10 to the power of 6. 1 by lambda equal to 1 by lambda equal to 49.2 into 10 to the power of 5. Then 1 by lambda equal to 49.2 into 10 to the power of 5. Then lambda wavelength is equal to 20.3 into 10 to the power of minus 8 meter. Then after a calculation, again it is written as 203 into 10 to the power of minus 9 meter. Therefore, lambda equal to 203 nanometer. Therefore, wavelength. He is asking us to prove the wavelength of incident light must be used in order to eject the electron with maximum velocity. That means when maximum velocity is given, what will be the wavelength? How much should I eject the wavelength of electrons? Then that is 203 nanometer. with this we end our video session. If you like our video, please like, share and subscribe to our channel Sri Guru Datta Education. Thank you.